Crystal field theory, lecture 67. Alright, show how the crystal field splits the D energy sublevels. Now the first thing is when the D, so these are the D sublevels, the d orbitals in the same sublevel. When it's a isolated metal ion, well, we don't see anything. We don't see or any splitting here. They're all the same, and we call these degenerate. When energy levels are the same for orbitals, they're called degenerate orbitals. Now, if we put them into a uniform electric field, negative electric field, say if the ligands came in, and there's 6 ligands, but if instead we had that electric charge spread out across a sphere, an ever decreasing sphere, in size it's decreasing, then the negative charge would come in from every direction, and that would be to the positive metal ion. That would be great. It would like that, so all of the levels would drop. The thing is that the ligands don't come in from every direction. They only come in from 6 directions. So when they do that, so that we don't get quite as much of a drop in energy, and what we get is a splitting. 2 on top, 2 d orbitals on top, and 3 on the bottom. So this is the true splitting, and the difference between here is del, and that's equal to the crystal field splitting. So a crystal is any periodic or organized set of ions, or it doesn't even have to be ions, any species that's organized. So the crystal field, the crystal means the 6 ligands attached to the central atom. That's very structured, and the field is the electric field they give off. And because they split they definitely lower the energy of these isolated d orbitals, but they don't lower them uniformly because the ligands aren't coming in from every direction at once, only 6. So we get this weird kind of splitting. So we should get used to seeing that, the 2 lines above, 3 below. And then we have the difference between those energy levels is the crystal field splitting. Now, we have high spin and low spin complexes. As you can tell, we have really endless variety of different kinds of complexes. In the metal ions inside, we have dozens and dozens to choose from, and each of them have different numbers of d electrons. So some have 0, some have 1, 2, 3, all the way up to 10. So if they have 0, then we don't worry about them. But from 1 to 10 d electrons, they will fill up these levels. Well, there's 2 ways of it happening. Either as we fill them up, well, I'll just do out the example here. If we have 1 electron, we have what's called high spin and low spin. And this is going to be low spin, and this is high spin. Now this is my choice to make the energy levels so different. Normally you wouldn't see that, they'd all be shown at the same distance apart. But I'm trying to show that this is a huge crystal field splitting energy versus this one. That for an electron to go from the lower state up to the higher state requires a lot of energy, a lot more than here. So this one is called high spin, and this one is called low spin when there's a big difference well, I can't explain anything more until we get into it. So for high spin, when this energy level difference is very slight, we still start at the bottom. And you can start over on the left, it doesn't matter. Any of the ones in the bottom are the same. We put the electrons in, we fill from the lowest energy on up. So here, it doesn't really make a difference. You notice they're exactly the same. The 1 electron in the bottom 3. When we have 2 electrons, we separate them. So far, we don't see any difference between high spin and low spin. It doesn't make any sense so far what we're talking about as far as those terms. 3, same thing. So it seems like I'm just wasting your time. So, well, they're all the same. We get to 4, though. 1, 2, 3, 1, 2, 3. When we add the 4th to the high spin, we have a choice. The 4th can pair up, which requires a pairing energy we call P. This is pairing energy. because electrons don't like to be in the same orbital together. They're the same charge. If they're forced to, they'll do it. So this electron, the fourth electron, can either pair up or it can go into the higher state. Now, it depends on the pairing versus the crystal field splitting. In this case, the pairing energy is greater than the crystal field splitting. That's true for all of the high spin. So that's what high spin means. The pairing energy is greater than the crystal field splitting. Low spin means just the opposite. There's such a huge energy change going from the lower level to the higher that the pairing energy is less than this crystal field splitting. So if that's the case where the pairing energy is greater, then the electron will go up to the next level. So if we think of it in terms of something that we can that every day, you have the choice of, do you want to room with somebody, or you want to on a lower level in an apartment complex, or go up to your own room at a higher level? Well, that requires more energy. So is it worth it? Well, if this guy is annoying, then yeah, you probably want to go up to the higher level. So the pairing energy makes it very uncomfortable for this electron to be here. Since it's such a small shift of energy to just go up to the next level, that's what it chooses to do. In this case, the fourth electron has a choice of pairing up, going into the same room or same orbital as an electron, or climbing up a lot more stairs. So in this case, the pairing energy is less than the crystal field splitting. So using our analogy, well, this person might be annoying, but it's easier to live with them than to climb up all of those stairs. So this person is aggravating, the electrons aggravate each other being in the same orbital because they're the same charge, but it's easier than climbing up those stairs. So now we see the difference. So with 5 electrons, 1, 2, 3, well, it's easier to go up here and then they'd be separated. And then this one, 1, 2, 3, 4, 5. Now notice here we have 4 unpaired electrons, 2 unpaired electrons. Here 5 unpaired electrons, 1. That's where the term high spin and low spin become clear. Here, when there's only 1, the difference between high spin and low spin, there is no difference. The crystal field splitting versus the pairing energy is still there in these are different complexes, but we can't notice the difference. Not until we get to 4 electrons do we notice the difference. So let's do 6. So there's a lot of ways I can phrase this. If I could just say that you have 6 d electrons in a high spin system. So you do 1, 2, 3. It's high spin, so you separate them. Now we have to come back down. We have no choice. But this one, or I could say you have 6 electrons in a low spin state. 1, 2, 3, 4, 5, 6. Now we have no unpaired electrons. We have 4 unpaired electrons. This thing is diamagnetic. This is paramagnetic. 7. 1, 2, 3, 4, 5, 6, 7. So for high spin, you fill up all of the orbitals with 1 electron, and then you start pairing up. For low spin, 1, 2, 3, 4, 5, 6, 7. You have to pair up all of these guys on the bottom. Put in 6 first before the 7th will go up to the top. For 8, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Doesn't matter how we fill them, now they look the same. And we saw that with 1, 2, and 3 electrons earlier. They're the same. And again, I've made this larger just to show the difference, but normally you wouldn't do that. On the exam, if I gave you blanks, I just put them like this. I wouldn't show any difference in the splitting. Just assume that from high spin or low spin you'd understand. 9, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9. Doesn't really matter now, but you should put half filled first and then then pair them. So 1, 2, 3, 7, 8, 9. So 8, 9, and 10 should be, and you can see this obviously is going to be, they're going to have the same number of electrons in each orbital because you filled them all up. So it doesn't really matter in this case how you fill them up. Okay, now, assuming the following species is high spin, show its d sublevels. Okay, so we got a little bit more work to do here. Iron, in this case, is +2. because the cyanides are -1 each, so that's +2 iron. Uh, 3D. Iron is would be this. Let me double check that. 1, 2, 3, 4, 5, 6. This is iron. Iron +2, we'd get rid of these electrons. So we have 6 D electrons. Those are the ones that we fill in. We said it's high spin. So 1, 2, 3, 4, 5, 6. That would be the high spin form. Cobalt is, so this would be +3. Cobalt, I'm not going to write out the full thing. It has, well, I guess I can. So argon, 1, 2, 3, 4, 5. 4s, 3d. Cobalt, so this would have 2 here. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Cobalt is +3, so we get rid of these 2. We get rid of this one. We have, so, yeah, 1, 2, 3, 4, 5, 6. Is that what we want? Yeah, 6. Okay. Just got confused there. Now this is low spin. So we're going to, low spin, we're going to fill up the lower level first. So they both have 6. That was just by chance. I think they both have 6, yeah. So they both ended up with 6 electrons just by chance. I just picked them. Hard to tell when you're drawing them. You know, well, it's not that hard, but I didn't bother to do it. So, but that's okay, because we can see the difference here. 6 high spin versus 6 low spin. Okay, use the Spectrochemical Series, I would provide that, to determine which of the following is low spin and which is high spin. Now the electrochemical series, I'm just gonna, well, I gotta draw all of it until we get to the 2 ligands. It's a bad idea to put them so far apart. That's okay. So we have cyanide, and I might as well finish up. This is CO. Here are our 2 ligands, the chloride and the cyanide. These are both +3 for the iron. So the only thing that's changed is the ligands, and I'm saying that one is low spin and one is high spin. Well, on this end we have weak bonding ligands. If they're weak bonding, then there's this would be a small crystal field splitting. If you want to go to the farthest extreme, like I like to do when they give you these kinds of the ranges, I say if it's weak bonding, let's say there's no bonding at all, then there's no splitting at all. So if it's weak bonding, then we'd expect a small splitting. If it's a strong bonding, that's what's on this side, strong bonding, then we should expect a large delta. So a small delta, we'd expect this to be high spin. And this is the one thing that gets students. And I know every time I do it, and I've taught this every semester for regularly for 12 years, and I've taught this for almost 20 years total. When I see high spin and small delta, I have to stop and think about that. Yeah, when it's small delta, when it's really close together, that means that we can separate the electrons, so that would be high spin. Large delta, go really extreme, then it's going to be low spin because the electrons are going to have a hard time getting up to the top, so they're going to pair up. So large delta means low spin. Small delta means high spin. And you know, that catches me even today. I have to just stop just for, it doesn't take me too long, just a couple of seconds, but I have to get it back in my head, that difference. So if we look here, we see that the chlorine for this guy is down the line. It's going to have a smaller delta than if you have the cyanide. Cyanide bonds very, very strongly. So we'd expect for this one to have a relatively small splitting compared to this one. And you don't have to write these out. I think what I'm asking, in this way. So which one is low spin? Well, this one would be the low spin. And this would be high spin. Now, to tell you the truth, since I wrote this question out, but I didn't do it before, the reason I'm writing all of this out is so that I don't make that mistake. We know that this is, they're asking which one is low spin and which one is high spin, assuming there's one of each. we know that the chlorine doesn't split the levels as much as the cyanide does. It's a relative scale. Cyanide doesn't split as much as the CO does, but since I intend to put the two ligands on opposite sides of the range so that there's no question about it. So this high spin, so the chlorine doesn't split the levels very much. The cyanide splits them very much. Since they have the same number of electrons, and I think it's 5 total, so is it, yeah, so 5, 1, 2, yeah, so it should be 5. This one would be high spin, it would be 1, 2, 3, 4, 5, and this one would be 1, 2, 3, 4, 5. Again, you don't have to go that far, this is just kind of a check that I'm using and kind of showing what happens, but just by looking at these ligands alone, you should be able to state that this ligand is weaker bonding than this one, so del is smaller, so it should be high spin, so this one should be low spin. Okay, and then the last thing here is we actually have a calculation. We haven't had one in a while. The splitting, the difference between them, if we have we can always boost a d electron up into the higher state and then have it transfer back down to fall back down into the lower level. So that transition will cause the production of a photon, or a photon can be absorbed. And when you have white light, the color that's absorbed is a complement of the color that we see. So it depends on what they're asking for here. So let's see what they're asking. A complex is an orange color. That means that its complementary color was absorbed. So if you look in the table that we have here, and I may get this table if I ask this kind of question, but most likely usually I just give you the crystal field splitting or the wavelength and ask you to find the other one. But orange light absorbs, means that the color that was absorbed was blue, which is 480 nanometers. So from the table I got that. So, and you said, well, isn't it a range? Yes, it's certainly a range of blue colors and orange colors, but we'll just go with that average number that they gave us. So it should be in the same, pretty much the same range, somewhere within 5% of each other. So we have, we changed the meters, and then we just plug it into this equation, and I didn't do it out. So what are they, approximately what we, oh yeah, so I said that, what is the crystal field splitting? Okay, so we found the wavelength. Yeah, I just have to finish up this. Luckily I have the calculator sitting here. I forgot that I had to do a calculation, because we don't do that many. So the crystal field splitting is 4.14 times 10 to the minus 19. So most likely I'll give you this wavelength. If not, I'd give you the table and you'd have to deduce it from that information about the color. And then if the crystal field splitting energy is this, what is the wavelength of light that it absorbs? So we know, so this is just the reverse, so 2.76 times 10 to the minus 19, 6.63 times 10 to the minus 34 joules seconds, 3 times 10 to the 8th meters per second, and then the wavelength. So it would be 2.76 times 10 to the minus 19 divided by 6.63 times 10 to the minus 34 divided by 3 times 10 to the 8th inverted, and wavelength comes up to be 7.21 times 10 to the minus 7 meters, or 721 nanometers. And that's it.